Okay, we're off. Today's screencast is going to be about intermolecular bonding and also a little bit at the end about lattices. And I'm going to try out using something like a highlighter today. So, we should be able to see highlighted the word intermolecular and bonding and lattices. And hopefully that will help us just guide us through this talk and you can see what we're talking about. Alright, so to just recap what we've covered already, we've been talking about how this kind of bond, a type of covalent bond, the polar covalent bond arises. And that's when we have two nonmetals which both have quite high electronegativity. So they actually want to attract electrons. And in this case we had hydrogen and fluorine. They both want to get extra electrons. But of the two, fluorine is the most electronegative. So when they share in a covalent bond, fluorine ends up having more of that share, the greater share. Okay, and so that shared electron spends, or a pair of electrons spends more of its time around the fluorine than it does around the hydrogen. Okay, so we say that polar molecules arise when the sharing of electrons in a covalent bond is uneven. The most electronegative element has the shared electrons more of the time, and that end of the molecule is the negative end. And we use a little delta sign to show that. So a delta plus means the most positive side, and we write that near the hydrogen on this valence diagram, and the delta minus is the most negative side. And that's if we see those, that indicates to us that there's a polar molecule, a molecule that has a positive end and a negative end. Okay. So we talked about that. We also then talked about, well, how all this then impacts on the bonding between molecules. So the covalent bond itself is within, it's an intramolecular bond, but because it then determines the charge or the distribution of charge on that molecule, the molecule then interacts with other molecules. Okay, interaction between is the intermolecular bonding. And the first kind was the dipole-dipole. So we get these polar molecules, in this case hydrogen chloride, and we'd show it over here, little delta plus and delta minus. It's a polar molecule. In fact, we say it's a dipole. There's another way of saying that. It has a positive end and a negative end. And when you get a lot of these molecules together, we get this thing called a dipole-dipole bond. So shown in these red dotted lines, wherever there's a slightly negative end, a chlorine, lining up with another molecule's positive end, hydrogen, there's an electrostatic attraction. And so that is what keeps these molecules together. Okay, and we get a dipole. Now, the dipoles occur in many covalent molecules that are polar, but not all of them. So here's an example of one that's polar and a dipole. So we're trying to represent here the distribution of electrons in these shared bonds. This is formaldehyde, and because the electron spends more of its time at the more electronegative carbon than it does with the hydrogens, the left-hand side of the molecule gets the delta plus, and the other side, the oxygen, is the delta minus. And in fact, the oxygen even has two lone pairs, which adds to the negativity. Okay, so it's clearly a dipole, a positive end and a negative end. However, carbon dioxide also has covalent bonds which are polar, because there's a difference between carbon and oxygen in electronegativity, and the oxygen side of each bond is the negative side, the carbon is the positive. But because the oxygens are symmetrical, and there's one on each end, there's no one side of the molecule now that is more negative than the other side. Okay, because it's symmetrical, although the individual bonds are polar, the molecule itself is non-polar. That's because the molecule is symmetrical. Polarity cancels out. One end is no more polar than the other. And here's another example of a molecule that has polar bonds, carbon tetrafluoride, very big in the dry cleaning business, or used to be, and again, each of the bonds are highly polar. Okay, fluorine is very electronegative, and so the fluorine ends are all delta minus. However, because it's so symmetrical, and you imagine this is in 3D in space, so they're all like a tetrahedron, okay, very evenly spaced fluorines, there's no one end that is more polar than the other, so you wouldn't call this molecule a dipole. Okay. The next part of this idea with dipoles is something called hydrogen bonding, which is just really another example of a dipole, but I would think of it as like an extreme dipole. And it only occurs, and you just need to remember these 3 or 4 elements. Okay, hydrogen is one, and if hydrogen ever forms a covalent bond with any of these 3, nitrogen, oxygen, or fluorine, we end up with something, a polar molecule that will give rise to hydrogen bonding. Okay, it's an extreme dipole. These 3 elements are the most electronegative elements, and what happens is they pull hydrogen's single electron. It only has one shell with one electron, okay, and that gets pulled right over to the other half of the bond, okay, and spends very little time around the hydrogen. Remember, the hydrogen has one shell, so if that electron is pulled away, it's just a naked proton. There are no neutrons. The nucleus has just got a proton, and that's obviously very positive. There's no shielding inner shell electrons or anything. It's just a proton. So in one of these kind of molecules, that hydrogen not only is delta positive, it's like just a pure proton. Okay, so quite positive. Okay, and so whenever you get an association between a hydrogen in one of these kind of molecules with the delta H with another delta minus, that's again a dipole bond, but we have a special name, the hydrogen bond. Okay, so it's the C1 in here with ammonia when it associates. We see it with water when that associates with other water molecules. Hydrogen fluoride, we also see that strong dipole. We call it a hydrogen bond because of the way kind of molecules that are involved. And lastly, the other kind of intermolecular, so these are all intermolecular forces, is something called dispersion forces. You might see them called van der Waals forces. It's the weakest of the 3. Probably hydrogen bonds are the strongest, then regular dipole, and then there's dispersion. Now, dispersion happens in with all atoms, with all molecules. Okay, and it just takes a little bit of thinking about. You have a look at this example of the Cl2 molecule, a chloride molecule. You'd say that there's a cloud of electrons. It's symmetrical. Okay, there's the same molecule, equal pull. So there's a simple covalent bond there, and we talk about a cloud of electrons. Now, if it's evenly distributed, there's no dipole, but electrons move. Okay, and they're random in their movement in many ways. And at any one time, there's slightly shaded. I don't know if you can see that when I highlight it. It probably hides it. But on the right-hand side, there's more of a density of electrons at one point than on the left-hand side. And very briefly, that side will be delta minus. Okay, at some instant, we say that's an instantaneous dipole. Okay, now the same happens for other atoms as well. Here's a noble gas, okay, xenon, which doesn't really form bonds at all. But even in the cloud around a single xenon atom, we could say that there is a side that at any one time, because of the orbiting electrons, is more negative than the other side. Okay, and then if we take 2 atoms, or this could be for any 2 molecules, there's one that's affected, one that isn't. If one comes near the other, okay, that negative side repels electrons in the neighbouring atom, and that side becomes more positive. Okay, so one polarizes the next, and we end up with having a raft of effect where you suddenly have a brief, instantaneous sort of electrostatic attraction between molecules, which is really just to do with the random movement of electrons and how they influence their neighbours. So it's quite a weak effect, but it is an effect that causes a bit of a electrostatic sticking together. So if you go to this website, periodic table, you can look at the slider arm of the temperatures of from absolute zero, move it up to higher temperatures, and you'll see that as you go down the periodic table, say for you look at the noble gases, helium, neon, argon, krypton, xenon, radon, they take increasing amounts of energy to change them from a solid to a liquid and then to a gas. Now, it doesn't take much energy, but there is an order, okay? And you'll notice that even more so with the group 18, in group 17, group 16. Okay, all of those nonmetals are harder and harder to make liquid and gas the further you go down. And what that's saying is they're getting bigger and bigger, those individual atoms, and they have more electrons. And the more electrons have more chances for instantaneous dipoles. So they get stickier, okay? There's more of this electrostatic attraction potential as you get bigger and bigger molecules or bigger and bigger atoms. If there's more electrons in the cloud, you get greater dispersion forces, greater chance of interaction, and forming a liquid or solid if it's cold enough. Okay, so basically big molecules are stickier with this weakest of all intermolecular forces, the dispersion forces. Okay. So this is sort of a bit of a ranking of all the types of bonding we've covered so far. Over here on, oops, I'm going to move that back again. Over here on the right is the strongest forces. Okay, we've got covalent bonding. So these are all within molecules, intramolecular. We've got covalent bonding, shared electrons, ionic bonding, electrostatic attraction of ions, metallic bonding, that electron C, or the glue that moves around and sort of holds metal cations together. And then over here on the left we've got the weakest forms, and we've got of those which these occur between molecules, intermolecular. Hydrogen bonding is the strongest, and then regular, which is extreme dipoles, okay, with hydrogen plus NO, or nitrogen, oxygen, or fluorine. Then we've got regular dipoles, polar covalent bonds that cause these normal, not as extreme dipoles. That's a slightly weaker intermolecular force. And then all molecules, all atoms have this dispersion force, and that's really the weakest though. Okay, so if there's any other kind of force, you'll see that before you see dispersion. But if you don't have these other ones, you will see the effect of dispersion forces. Okay. So just briefly talk about lattices. So when you bond covalent bonds in 3 dimensions, you can end up with a couple of kinds of lattices. There's a network lattice, which extends in all directions, which is like diamond. For example, carbon bonds forming 4 bonds with other carbon bonds going off in all dimensions. Very, very strong. Okay, so these things have high melting temperature, they're very hard, don't conduct electricity, they're unreactive, everything's locked in place. And then the other sort, which is again an example with carbon, is a covalent layer lattice, and you get this, and this is something that's an example of graphite, okay, which is just in a layer you have this lattice. So you can see these hexagonal sets of bonds all going off in 2 dimensions, so very strong covalent bonds within the lattice, but between the lattice, shown in orange here, you get very weak intermolecular bonding, which is really just dispersion forces. The free electrons, again, that are orbiting around and sometimes, you know, make one area more positive, one area more negative, and you get this association, okay? So in graphite, you get very strong within the layers, but weak between the layers, and that makes them soft. That's why graphite is so good, you know, in pencils, etc. Okay, because the layers can slide past each other. It actually feels quite greasy if you get a lot of, you know, sharpened pencil sharpenings on your fingers. It actually feels quite greasy. And in fact, they can conduct electricity. If you do a strong enough, you know, pencil line on a piece of paper, you can connect up electrodes to it and conduct electricity. It's relatively unreactive, though. In graphite. Okay, so there's 2 different kinds of lattices then that occur. Alright, we'll leave it there, and hopefully this has been of use. Thanks.